Good evening. So we'll start today's session, and if other people are joining, they can join subsequently. So I've shared the screen, and today we'll be continuing a little bit of the week 10 lectures after what we have discussed yesterday, and then we'll start the week 11 lecture slightly and then continue it in the upcoming sessions. Yeah. So welcome to this course. Uh, and today we'll be discussing the topic topographic section or elevation profile or cross section or longitudinal section. So these are the names that can be used hand in hand. Like it's not like whenever they say a topographic section or a cross section, that more or less means the same. So, what does or what do we get in a topographic section? So, it basically shows elevation as a function of distance along the profile route. So, it's a function of distance in a like we say elevation profile kind of thing. And in that we are determining this topographic section as a function of distance. Topographic profile along a straight line is easy to create. Like if something is on the surface, if something is straight, that is very easy to generate in a topographic profile. But if you have a topographic profile like a drainage line, so now you know that drainage is basically what like the different directions in which a river flows. It can be tributaries, distributaries, anyway that is not going to be a straight line, right? It's going to be very, very spread out and very not very straight. So in such cases, we need the GIS using them in order to generate the longitudinal section or the topographic section or the topographic profile. So here we have this image. So a topographic profile shows elevation as a function of distance along the profile route. So what is this profile route? For example, let's say we have this drainage system that is shown here. So here we have a topographic profile in a straight line. Okay, this is the red color one. Now, and when you go say in any software, you can find a terminology for this as like a, as a drawing a cross section or a topographic profile, anything, and that is basically easy for a straight line. So if here you can see, I should have actually zoomed in a little bit, but here in the x-axis, we can see the distance. We have the distance. So suppose the direction that we are moving for the profile is from west to east. Okay, so this is west and this is east. So this red line is the topographic profile, and on the x-axis we have the distance from west to east. So from here, this point will be 0 for us, and this will be the maximum distance, however, how much ever that has been covered in this entire straight line. So here you definitely have this x direction. Then you can also maybe find the y direction of like y point for that particular point, xy coordinates. And then along with that, if you can add the elevation factor like the z factor, then actually you will be getting a three-dimensional topographic profile. If it is just like you're taking into account x and y, then it is a two-dimensional uh, system in which you are seeing the topographic profile. One minute. Okay, so here you can see we have the 2D length and here we have the 3D length. Now from here you can see that the 3D length is more than the 2D length. So that is basically, the effect is from this Z max, Z minimum, the length uphill, length downhill, all these parameters when they are incorporated. Like for example, from yesterday's session also we had discussed that there are certain, if you have a flat terrain kind of thing and if you look at the grid, okay, if you remember, like we have the square grids, right? So there the area covered by this square grid on a flat profile will be less than the area covered along a slope. So the thing is, in the slope, that rectangular, instead of that rectangular grid, we might have something like this, which has an area more than that. So here what you have to understand is, in case of the 2D length, we don't actually consider much of the elevation parameter, because of which the area is not as much. But when that the third dimension is also taken into consideration, the area will be more. That is why the 2D length is less than that of the 3D length. So it's basically what is written here. Topographic profile is shows elevation as a function of distance along the profile route. So this basically the output what it is giving is from here to this point, this is how the elevation is varying. Then next we want to have this cross section which is along an arbitrary line. Here we don't have a straight line. If you look at this, this is a green line that is shown here. That is a very arbitrary line. It's not a straight line. So along this arbitrary line, it's not very easy to generate the section in most of the even by the softwares, let alone doing it manually. It's quite difficult in some of the softwares also. So we have to find a specific tool for that. Otherwise, it is going to be difficult. So here you have a similar profile that is shown here. So like in the software like ArcView GIS, along this drainage line, a cross-section profile has been drawn. So starting from here, we have, where is the X? I don't think it has been marked here, but X and Y parameters will be obtained for this, just like how we had done it for the previous one. Anyway, the only thing that you have to keep in mind is we can have certain functions or tools in these softwares which will help us generate this profile section along a arbitrary line. But then at the same time, if if it's a straight line, it's more or less possible in almost any of the softwares. But if it's an arbitrary line, only we can do it in properly in softwares and not by using the topo sheets. That's going to be difficult. So the biggest advantage of having GIS and the DEM, the digital elevation model, is to get a topographic section along any arbitrary line. So in case of geology, like geologists always try to study these geological cross sections. So there the topographic profile will more or less always be a straight line. Like they barely make use of any arbitrary line cross sections. So they have to first get the elevation values, which they generally get by these contours, and based on those contours the topographic profile is first drawn, and then we have these different rocks, lithologies, all those are incorporated into that section. Now here we have this diagrams which sir had given, which is about characterizing microterrain features. So we have two things here, which is one is deviation from trend and the other one is localized deviation. So the first one is they're talking about a useful approach to identifying the microterrain features. It involves subtracting a smooth elevation surface, which is what you're seeing here. See, there are no uneven surface, right? This red one that is going here, red dotted one. So that is a smooth elevation. More or less they are getting a, what do you say, a weighted average, or like a sort of like a median kind of thing. So that is what that is being generated here. So that is um, what we do is we subtract this smooth elevation surface from the actual elevation surface. So the positive difference values indicate convex features, negative indicate concave features. The magnitude of the difference indicates the relative height of the microterrain features. So this is like very small features that might be on that surface. In order to identify that, first we need to have a smooth elevation for that profile. Then we also have the proper elevation profile. Then what will we do? We will subtract that, and when we subtract it, we might get positive difference or a negative difference. Positive difference indicate the convex features that are present here, which is like the elevated one that is shown here, which is above the smooth elevation. And then the negative differences that you get gives you the concave features which are below. So based on this, we can actually delineate the microterrain feature in any of these profile sections. So based on this, we can actually, along a line, we can say like if a terrain is smooth or if it is having some roughness. Because this is not like you're having a very big hill or anything. These are like micro terrain features. So we need to do such things to ascertain like how elevated or how depressed those that surface is. Then we have the next one, which is the localized deviation. So another approach for identifying microterrain features subtracts the elevation value at a location from the average of its surrounding elevation values. Positive deviation values indicate convex features and negative indicates the concave features. The magnitude of the deviation indicates the relative height of the microterrain feature. So if here what they do in this particular case, here they had just subtracted from the smooth elevation and the elevation profile, and then they were finding it. Here we don't have the smooth elevation. Instead, what they're doing is at a location, like for example, if this is the location, what they're doing is like they take an average from the surrounding values, like the surrounding values will be 112, 114. So they will take an average of this, and that average will give you what do you say, there are one, this is the value 1 2 3 4 5 6 7 8. Okay, these 8 things that we are adding, and then we divide it by 8, so we get the some value, and that value we subtract with the 100, and that is going to give us the difference. So if that is a negative one, we are getting a concave feature, and if we are getting a positive value, we are getting a convex feature. So that is how the micro terrain features can be characterized. It can be characterized by either doing the deviation from trend method, or it can be characterized by using the localized deviation. The applications of topographic profiles include the surface roughness along a line can be explored, which we had already seen. Like, you know, you have a map or something like this, and you have a topographic profile, a straight profile. For the time being, we are considering a straight profile. So along this straight profile, from this point till this point, we are actually determining how the elevations have been or how the topography is, we will also include the uh, the uh, ruggedness of that or the roughness of that surface. It provides information about microterrain features, just like how we have seen now. It is very useful for geological cross section. So if you know, like if you have familiar with geology, we can see that especially in field geology, they make use of such cross sections in a very big area. So that in that sense, topographic profiles are useful. And the topographic profile along a drainage line can provide information about rapids and falls. Rapids and falls is like, we have these waterfalls kind of thing. So its smaller version is the rapids. So those things like, in a drainage profile, it's not necessary that the river is going to just flow like this. At times, it might encounter a small rapid or a big waterfall. So such changes we can actually understand if we can map the topographic profile. Then these falls can provide preliminary information about feasibility of a small hydropower site, because as we have seen and we know that the energy of that water in that flow of water or waterfall, that is quite high. So it is a potential site for hydropower site, right? So instead of having to go to each and every location to find out such a site, if you can generate a topographic profile for that area, you can actually understand, okay, where this is feasible, like if you can introduce a small hydropower in that area or not. So such things, the thing is, like, the main use of GIS by now you would have understood, right? If it's a small scale thing that you need to do, then you can do it manually by going to each place. But if it involves a huge data set or a huge area, that is when the GIS actually comes into use, because in such situations it's not possible for us to do everything manually. It can have human errors. So in order to eliminate that, we can actually make use of such applications in the GIS. Then another derivative, DEM derivative, is the surface volume. So basically the surface volume, it calculates the area and volume of the region between a surface and a reference plane. So here also we are actually making use of a reference plane. So that reference plane is this blue line that you're seeing here, okay? And this here you can see a mountain kind of feature. So the reference plane is set to above the plane height location intersects this surface. So whatever the empty space or something that you have above this line, that is being marked over here. So surface is shown in gray. So here we find that this area has to be cut, whereas like this area has to be cut and this area needs to be filled if this is the if we are considering the region above this reference line. And then based on that, we can actually calculate the area and volume of the region between the surface and the reference plane. So the cut and fill analysis is basically a part of the surface volume analysis. That is like if you cut something from an area, you need to fill the other areas with that, whatever you have removed. So it is basically a procedure in which the elevation of a landform surface is modified by the removal or addition of surface material. Okay, so you can either remove the material from an elevated area, or you can fill material in a a depressed area. So the areas and volumes of change are then summarized. The basic calculation is the difference between the desired elevation and the original elevation. So here you can see this is the original elevation that is shown here in brown line, and this black line is the proposed elevation. This is how you have to do. Now if you have to reach this proposed elevation that is shown here, then what you have to do, like for instance this area of that original elevation is actually lying below the proposed elevation, right? So in that case this small area needs to be filled with the material, but at the same time you can see this much of area is above the proposed elevation, so that needs to be cut. So actually you can cut material from here and then you can just use it to fill the areas that are below the proposed elevation. Then here also we are actually removing, here you are removing and here you are filling. So you need to basically attain this proposed elevation by doing the cut and fill method. So this is very important in case of many civil engineering projects. Okay, so like sir has also mentioned it. So many civil engineering projects, it will fail because they are like in the initial stage itself, they are unable to estimate the earthwork that is required, and when the projects commences before this is actually done, then they realize that, oh, like this much of material has to be removed, this much has to be filled, and if that groundwork was not done initially, then they are going to face a trouble. So the better thing is to do cut and fill analysis as many times as possible in order to get a very good idea regarding how your proposed elevation needs to be attained. So by taking surfaces of a given location at two different time periods, it identifies the region of surface material removal, addition and areas where the surface has not changed. So this is showing you a diagram over a period of time. So in 1980, this was the original state of that surface, where you can see there are some ruggedness, some depressions and all those things. Then in 1990, which means 10 years later, surface after a period of time where erosional and depositional forces have acted on it. So what has happened to the surface over here? You can see this region, uh, you know, sediments have been eroded. Like if you can see, this small elevation is not here anymore in this region. Okay, so that means surface has been eroded in this area. This depression you cannot see in this one, right? So which means some kind of deposition has happened here, which made this area more or less smooth. Okay, then you can definitely see that this area is not at all there, or rather it has been reduced. So which means a lot of material has filled in this area. And then this side also you can see that much of ruggedness is not there, which means again some sort of erosion has happened. So this is how you actually understand that surface. So surface in 1980 was like this, but then after a period of time, erosional and depositional forces acted on it, and that surface changed. This most of the time what happens is this, you won't be able to understand it very well, but if you have some kind of information from that 10-year ago period and then 10 year later, you can actually make the comparison and understand where and how the erosion and deposition might have happened. The applications of cut and fill analysis involves identifying regions of sediment erosion and deposition in a river valley. Now you have to understand that the river valley, it's like in a very large scale. So if you can do this cut and fill analysis, you can actually sort of understand like where in that river valley the sediment erosion or deposition might happen. So you can actually identify those regions. It calculates the volumes and areas of surface material to be removed and areas to be filled around a mining site. So you know that in mining site we are basically digging up the land. So if we can do a cut and fill analysis, we can actually estimate how much of material needs to be removed, like the volume or the area, and then where this removed material needs to be filled along, around that mining site. So this is the another application of cut and fill analysis. Then it is also used to identify areas that become frequently inundated with surface material during a mudslide in a study to locate safe areas of stable land. So in regions where this mudslide is a type of mass movement, kind of like a landslide. So based on this cut and fill analysis, we can actually identify the potential locations where the surface material can, get covered by this mudslide, covered by surface material during a mudslide, and thereby ascertain the safe areas where, safe areas or stable land where relocation can be done. The cut fill tool create a map based on two input surfaces. So one is the before one and one is the after one. So in order to create a map, we need this kind of information. One, a before information, and then another an after information, displaying the areas and volumes of surface material that have been modified by the removal or addition of surface material. So like the example that I showed you, that area in 1980, then that area in 1990. So now we know, right, where that potential locations of erosion is and potential location of deposition is. So for that purpose, we need these two information, a before information and an after information, in order to understand that area better. And the important thing is this before surface, after surface, that raster surfaces must be coincident. It's not that it should, one is slightly smaller, the other is bigger, because they must have a common origin. The same number of rows and the same number of columns, same cell size, only then can we make the comparison. If that number of cells is different or the cell size is different, then the comparison cannot be made properly. So for accurate results, the Z units should be same as the XY ground units. Like if you are doing it in a 3D manner, then that Z unit should also be the same as the XY units. This ensures that the resulting volumes are meaningful cubic measures, like in cubic meters or anything. So this unit is also very important, like in what scale are you actually getting those measurements. This brings us to the next derivative, which is the topographic roughness. So it is the relative topographic position, also called the topographic position index. It's a terrain ruggedness metric and a local elevation index. The topographic roughness or ruggedness is defined differently depending on the calculation used. Like basically from that name itself you can understand it is talking about the roughness of a particular terrain. So that can be determined using this topographic position index also, that is using TPI, that is the topographic position index, at different scales and slopes. We can actually classify the DEM into slope position or the landform category. Just a minute. So in case of a DEM, like like we can classify a particular DEM image. So here it can be done based on the slope position, like you can classify it in which the classes will be ridge top, valley bottom, mid slope, etc. Or you can even classify it in terms of that landform, which may be canyons, valleys, plains, open slopes, mesas, etc. So the TPI is the basis of classification system, and simply it is the difference between a cell elevation value and the average elevation of the neighborhood around that cell. So what we had seen earlier also. So a particular cell might have some sort of elevation value. Then what you do is you find the difference between that value and the value surrounding that particular cell. Average of elevation surrounding that particular cell. So if that difference is positive, like that you're getting a positive value, that means the cell is higher than its surroundings, while negative values means its position is lower. So what I'm trying to tell you is like if you have a very simple 3 by 3 grid like this, okay. So this is the cell that I'm going to do this position analysis, okay. So what I do is, like, let's say this region has some sort of value, say x, okay. Now what I'll do is I'll take an average of all the elevations that is surrounding this x, which is basically this 8 cells that are surrounding this x cell. Then what we do is this value that already that cell has, we'll subtract it from this average value. Now if that resultant value is positive, what does that mean? It means that this particular cell is higher than the surrounding cells. At the same time, if this is negative, that means this cell is basically at a lower level when compared to the surrounding cells, which means you can actually say if there is a hill or a ridge or a valley or something like that. If it is significantly higher than the surrounding neighborhood, then it is like, that's what I was trying to say. If it's just slightly higher, that might be just a small surface roughness, like a normal one, which is not very evident. But if it's really high, that might indicate that this could be at or near the top of a hill or a ridge, which will be definitely higher than the surroundings. Significantly low values will tell you that it is at or near the bottom of a valley. TPI values near 0 could mean either a flat area or a mid-slope area. So it's most likely like, it might not be like you're getting an exact 0. So something close to 0 suggests that that particular cell is more or less very similar to at an elevation similar to the surrounding cells. So here, like sir had also given you a diagram, which is, I think, easier to keep in mind instead of reading all these things. So I'll just draw it here so that mm, it's a sort of a recap. So if we have a scale or a line like this and the midpoint is 0, so if you go towards the right, it is positive, and if you go towards the left, it is negative. And here we are talking about the position index. So positive TPI, and here we have the negative TPI. So at 0 we have what? Flat areas mostly, but at times the slope might be shallow also. So it's not that it's absolutely flat, but not very steep either. And then towards this direction, if it is going, that means it is like probably going towards a valley kind of thing. And if it's getting more positive, then it might be hill kind of thing. So this is just an image that we can keep in mind in order to understand what positive TPI means, or what a zero TPI means, or what a negative TPI means. Another thing that you have to keep in mind is that this topographic position index, it's very scale dependent. So and by scale dependent, what I'm trying to say is, like, for example, if you have an image like this, okay, something like this, and we have a point like this, okay. So if in the first case we are just considering this much of area, then what is the thing, like only this much area I'm considering, okay. So that means only this much, which means the TPI can be mostly approximately equal to 0, because there is no much elevation or something like that over here. But the moment you increase the scale, okay, just a minute. Okay, so this is the first one, the red line, that is the first scale. Now if I increase the scale slightly like this, then what happens? Now here we have some depression, and then this point is at a sort of elevation, which means the TPI will be definitely greater than 0, right? Because the surrounding area is small and then this area is elevated. So TPI will be greater than 0. Now if I again increase this by, like, let's say if I okay, now if I again increase this, like this much area, if I'm considering, then what will happen? This is basically a little more above, I'll take, okay, this much. So this is basically staying in a depression kind of thing, which means in a valley kind of thing. So the TPI will be less than 0, negative. So what I'm trying to convey here is that the topographic position index is very much scale dependent. So it actually depends on the area that you are considering. So that needs to be specified also. If you're taking a very big area or just a small area, that needs to be specified, only then can we make some kind of comparison. So this scale is always determined by the neighborhood that is used in the analysis, like how much area has been covered. This brings us to the terrain ruggedness index. So this is sort of like a variation to the TPI, or the terrain position index. So this provides a rapid objective measure of terrain heterogeneity. Heterogeneity means the terrain will not be smooth. Like when we say homogeneous, that is more or less like very smooth terrain where you don't have that much of elevation or depressions. But heterogeneity is basically talking about the ruggedness of that terrain. So, or the degree of irregularity of the surface, that is what roughness means. So, it's calculated by the largest intercell difference of a central pixel and its surrounding cell. The determination of the roughness plays a role in the analysis of terrain elevation data. It's useful for calculations of the river morphology, in climatology, in physical geography in general. So the main difference, like as I said, TRI is a variation of TPI, but even then there might be some difference, right? So the main difference between TRI and TPI is that TRI is the mean of absolute differences between the value of a cell and the value of 8 surrounding cells. So you have a value of one cell, like I'll just change it. Okay. So let's say, again I'm just showing you an example of the 3 by 3 grid, okay? So we have a 3 by 3 grid like this. So absolute differences between the value of a cell and the value of 8 surrounding cells. So if I'm taking this cell at the middle. So this cell minus each of the 8 surrounding cells we'll take. That whatever difference that we get, we take the mean of that. So that is the topographic roughness index. But in topographic position index, it is the difference between the value of a cell and the mean value of the 8 surrounding cells. So in the first case, that is in the roughness index, we are actually subtracting this value with each of these values and taking the mean of that difference, each of the differences. But in the TPI, what we are doing, we are again like taking the difference, but here we are taking the difference of this cell value with the average of all the remaining 8 surrounding cells. The value of TRI are lower in flatter areas but high in both steep areas and in steep rugged areas. Obviously roughness is more, that's why. Topographic position, example like valley bottom, mid slope, ridge top can provide valuable information about the geomorphology of the region. Roughness is the difference between the maximum and minimum value of a cell and its 8 surrounding cells. Then we will discuss a little bit on this hill shading part. So a hill shade is a grayscale. Grayscale means black and white kind of thing. So a grayscale 3D representation of the surface with the sun's relative position considered for shading the image. So it's more like, you have a 2D image, but it is made into a 3D one based on the sun's relative position and how the shade is coming. So shaded relief or hill shading, it simulates the cast shadow thrown upon a raised relief map or more abstractly upon the planetary surface represented. So for example, like let's say you have terrain like this, something like that. Okay. So if the sun is over here, then definitely this area is going to seem really bright. At the same time, this area, you may not see it as that bright, right? This might be dark. So that kind of shading is taken into consideration in case of the hill shading or the shaded relief model. The shadows normally follow the normal convention of top left lighting, in which the light source is placed near the upper left corner of the map, something like this. Based on that we need to fix that position of the lighting, and based on that only then can you actually understand like in which side that depression is there, or like where that light is reflecting properly. That kind of thing can only be ascertained if you can actually fix the position of the lighting. So that is by normal convention, that is always in the top left of the map, upper left corner of the map. So now if a map is oriented with north at the top, the result that the right appears to come from the, I mean, the light appears to come from the northwest. Okay. So like you have a map like this, and this is the north. So in terms of that direction, definitely the lighting will have to come from the top left corner, right? So that will be from the northwest direction. However, this is unrealistic for maps because the sun does not shine from northwest direction. So this is an sort of like an assumption kind of thing because this is not realistic. Therefore, the normal convention is followed to avoid false topographic perception phenomena. And why I said that this is unrealistic? Because the sun can never reach this northwest location. It's like most of the time it will start from the east, like we know, and it goes to the and it will set in the west. So it's not possible for it to reach the northwest part. But because we are working on the computer, we can actually simulate that in terms of this, reference with the north, and put it where as per our desire. Although technically or realistically, this is not the case. So as I said, hill shading is an effective technique which gives a 2D map an impression of three-dimensional appearance. And this is always achieved using a single point source of illumination. Like that single point source needs to be there. It cannot be from all sort of directions. So that single point source of illumination is very much necessary for the hillshade model to work. So here I've taken the slide exactly as sir has given. So here we are trying to explain how the hillshade works. The hillshade raster has an integer value range of 0 to 255. Okay, so total you will be having 256 values. So it's starting from 0 to 255. So this is the input raster that you have, INRAS1, and here we have the values. And because it's not going to be like 1 2 3 all the time, but here for simplicity it has been given like this, 1 2 3. And we also have a gray cell which is basically telling you no data. So this is the input raster that you have. So one thing you definitely have to keep in mind is if the input is no data, the output is definitely going to be no data, and there is nothing else that is going to be incorporated there. So what happens is the analysis of shadows is done by considering the effects of local horizon at each cell. The raster cells in shadow are assigned a value of 0. The Z factor is essential for correct calculations when the surface Z units are expressed in units different from the ground XY units. So here that elevation factor is really important, because if that is not available, we cannot actually understand how the hill shading is there in that particular location. So that needs to be like it's very essential for proper calculations in the output raster. Now the hillshade parameters are the primary factor when creating a hillshade map for any particular location is the location of the sun in the sky. So the most important thing that you always have to keep in mind whenever you hear the term hillshade or something related to that shaded relief model is that it is always dependent on the position of the sun in the sky. So when you talk about azimuth, that is basically, it is the angular direction of the sun measured from the north in clockwise direction from 0 to 360 degree. An azimuth of 90 degrees is east. The default azimuth is 315 degrees, which is northwest. So what it actually means is, if you have the directions like this: north, east, west, south, we know that for conventional purpose we consider that the light is coming from the northwest. Okay, so in that case, how do you measure the azimuth, or what is the azimuth? It is the angular direction of the sun, which is measured from the north in a clockwise direction. So this is the north. We need to measure it in the clockwise direction to this point, because that is the northwest, right? So this much of angle, how will it be? Like this point in north is 0 degree, and if you complete a complete clockwise circle, then it can also be 360 degree. East will be denoted by 90 degree, south will be 180 degree, west is 270 degree, and again, as I said, if you complete a whole circle, it is going to be 360 degree. So if we are, as per the convention, if we are considering that the position of the sun is in the northwest, then how much angle would this be? It will be somewhere around 315 degree. So that is the azimuth. Okay, the azimuth for hillshade. That is why it is given here. Default sun azimuth for hillshade is 315 degree. So this you have to keep in mind. Why is it 315 degree? Because we are saying for convention purpose, we are considering that the sun's position is in the northwest part. But you also have to keep in mind that this is an unrealistic approach, because the sun position is realistically not possible in the northwest position. But then for this purpose, for doing the hillshade or for preparing the shaded relief model, this needs to be considered. The altitude, it is the slope or angle of illumination source above the horizon. The units are in degrees from 0 to 90. The default is 45 degrees. So default sun altitude for hillshade is 45 degrees. Like that is, if you consider this arc to be the horizon, so it varies from 0 degree from the ground to 90 degrees just vertically above. So the default location or the altitude considered for hillshade is 45 degree. So these two things please keep in mind, that the sun azimuth is 315 degree for hillshade and the default sun altitude is 45 degree for the hillshade. Okay, before the problems, like I could only prepare the slides till this part. I thought I'll also include the slides that sir has prepared. Just a minute, let me just open it. Okay, so till here I had prepared, and the remaining we'll just continue so that I don't leave it halfway today. That's why I'm just continuing here. Okay. So here you have an example that we'll cover. Uh, so in both these cases, the azimuth is the same. Okay. The sun angle or the altitude is what has been changed here. So that difference you can actually see here, right? Like this is the low sun angle and here you have the high sun angle. So what happens is, like this even you can also understand, for example, if at in the afternoon, like, or in the noon time at 12 o'clock, we know that the sun is going to be directly above us. So if that sun angle is directly on top, then the shading will not be as much. You will not see that much shaded areas. But if it is at a low sun angle, like if it's at some angle, not exactly on top, then what happens? You will see more shaded regions. That is what you're seeing here. When low sun angle is there, you're seeing more shadows, right? Because that sun is at an, at some angle which is less than 90 degree. But then in this case, it is more of a high sun angle. So in that case, you're not seeing as many shadows. So the position and the altitude or the sun angle is very important in order to generate a good hill shade model. So how is the hill shade calculated? So to calculate the shaded value, we need to first determine the altitude and azimuth of illumination. Okay, so that needs to be known. These values will be processed with calculations for slope and aspect to determine the final hill shade value for each cell in the output raster. So the thing is, when you're generating any kind of hill shade, of course, the prior importance should be given to understand the altitude and the azimuth of illumination. Okay, illumination source, that is basically the sun. So that altitude and azimuth definitely you need to know, but at the same time you should also have some understanding or some values regarding the slope and aspect also, because it's not necessary that all that surface is going to have the same slope or same aspect. So you need to have that information. Then once you have that, the algorithm for calculating hillshade is as given here. So here you have to understand that the cosine of the zenith, uh, the slope, the azimuth and the aspect. So all these things, they are also given in radians. Definitely it's not in degrees. So that's what I was trying to say. Like whenever you're doing any kind of calculation, you have to keep in mind that like you have some kind of idea regarding the units that are used. And another thing that you have to keep in mind is that if the calculation of hillshade value is less than 0, that is, it's some, for instance, you are calculating hillshade and you're getting a negative value, the output cell value will be determined as 0 and not like you don't put that negative value there. And here, as I said, we this zenith, the slope, all those things are in radians. So the radian is basically it is equivalent to the angle subtended. Like this is a very mathematical thing. So I'm just uh, telling you what is given here. So it is equivalent to the angle subtended at the center of a circle by an arc equal in length to the radius, which is always about 57 degrees. Like I don't think that much of detail is required for now, but if you want to understand what radian is, you can actually go through this. Uh, Then we have the multi-directional hillshade. So the other one, like it's more of a simplified one. Traditional hillshades are created by illuminating light from the northwest direction. So this often produces results in which the illuminated sites are overexposed and terrain details on non-illuminated sites are obscured. Obviously, because wherever from that northwest direction, as I had drawn earlier also, I won't be able to draw in this one, that's why. But what I'm trying to say is, like, if you have some kind of a hill structure, uh, let's say I'll add a slide here. Okay, so let's say you have a hill structure like this, something like this. Okay, and the sun illumination is coming from this direction. So what happens is this area will be overexposed. This area will the light is directly falling in that area, and whatever this area is going to go in the shade. So what happens is this slight roughness that is shown here, even that won't be accounted if we are doing, going for this conventional method where we are considering that the sun or the point source of light is coming from the northwest. Okay, like that is the easiest way that you do, but it's not very accurate in all the cases. So this issue persists even more in areas with medium to high slopes. Okay. So what happened is that this is going to give you a not so realistic output of a particular region if this is how you're going to do it. So Brassel in 1974, the person recommended setting a variable light source direction for each cell based on a primary illumination direction plus or minus a directional adjustment computed from the aspect of that cell. So for each cell, instead of just considering for the entire cells single point of illumination, they said we'll consider each cell and then decide the light source direction. Brassel also recommended that the illumination angle, inclination angle, that is how high the sun is, like the sun angle, for each raster cell should be variable based on the deviation of the surface normal to the primary illumination source. So all these parameters that we just considered for the whole grid, instead of doing that, what the person suggested was, in order to take into consideration the variation in each cell, because as I drew and show you, such small variations may not be accounted for if you just go for the conventional method. So each cell needs to be considered. So by this method, every cell could receive a hillshade based on a different illumination angle. But the thing that you have to keep in mind is, like, this was a recommendation, but however, so far this has not been implemented because it's quite complicated. Like, if you are considering a very, very big area, and if the number of cells are so many, it's not very feasible to do this for each cell. But if you are able to do it, then you're going to get a very accurate hillshade model for that area. So instead of although this Brassel method could not be implemented, Robert Mark's multi-directional oblique weighted method was implemented. In this MDOW method, the landscape is illuminated from 4 directions, each separated by 45 degree and covering a range of 135 degree. So all 4 directions are being considered here. By this method, the hillshade generated by each of these illumination sources is then weighted according to the aspect of that cell. So for getting a little better output, what you have to do is that, of course, you will have an output generated based on illumination from 4 directions. But then that is again compared with the aspect of each of the cell, and then you finalize a hillshade map for that region. The cumulative effect produces a hillshade illuminated generally from the average of the 4 illumination directions. So this is a graph which is taken from the Mark's original graph. It shows the weighting of for all the 4 illumination sources based on the deviation of cells aspect value from the cumulative direction of the illumination. So we have one illumination source over here shown in blue, then this illumination source 2 shown in purple, the one that is shown in red is the 3rd illumination source, and then the green one is the 4th illumination source. And then you have these aspect deviation from the primary illumination. So this is the effective direction of illumination that is shown here. It's kind of like an average of the 4. So by modeling the shade, what we are calculating is the local illumination and whether a particular cell is in the light area or the shadow area. Then when you model the shadow, we can actually identify each cell that will be in the shadow of another cell at a particular time of the day. Okay, because the sun's position is going to change, right? So the region that, like, it's very rare that a region in the shadow is going to be always in the shadow unless it's that that much away from the light source. But if you consider a point, it's not going to stay in the shadow throughout the day because the sun's position is going to change. So when you model the shadow, you can actually understand how that region is, the shadow in that region is going to change at a particular time of a day. So this is a soil map with hillshade. So it is often useful to use a hillshade raster to show terrain, to support other information in a map such as an analytical surface like population density or a thematic overlay like soils. Most of the time we have a black and white hillshade that is generated, but then we can actually give the colors to it and obtain a colored hillshade. And then what is done here is you have a dam of this drainage. Now when you actually combine this hillshade and the dam together, you can actually see a colored hillshade with the drainage. So from this, you will get a lot of information if you're studying that how the drainage is spread out, how that water is moving. So just the drainage map alone is not going to give you much information, but when you actually combine it with the hillshade, you can get more information regarding that area. So this is an example of the San Andreas Fault in the United States. It's a very seismically active region of the world, and we also have another seismically active region in our country, that is in Gujarat, the Kutch region. The Kutch earthquake, like that is a very active area. So here also you have these hillshades in the background. So here, why this, in integrating this, like of course we can actually get a very flat map without the hillshade map. We can actually see where these faults are. But with the hillshade map, we can see that where you have this fault line, here also and here also, you can see that they are creating a depression. And because of these fault movements or the earthquake generated along these faults, there will be high erosional activity. So that kind of information you're getting because you combined the fault line along with the hillshade map. So with that you can actually see that in both these cases, in this case also and in this case also, we can see that fault line that is staying in a depression where the erosional activity is more. So this what I'm just trying to convey, like, or what this entire course has tried to convey till now, is that you may have a lot of informations, right? Like you may have information regarding the population, you may have information regarding this fault line, you may have tons of information available. But if you have some idea with GIS, Geographic Information Systems, you can basically combine all these things together to model a realistic scenario for whatever your purpose of study is. So that's how the GIS comes into use or help. So this is basically showing you where earthquake of magnitude 7.3 occurred in Nepal. Mm. And just by representing it like in a very flat map, if you can actually show it in a shaded relief model in the background and then overlay this region like where the displacement was caused due to the earthquake, then you'll get a little more clearer picture of how that region was affected. This is a similar one, I think, of another earthquake that happened in Kathmandu, like in Nepal. So this is showing you a comparison between a standard single direction hillshade that is shown on the left. Standard means what? You have a single point of illumination. Okay, and the new multi-directional hillshade. Notice how the multi-directional hillshade enhances the expressionless regions and accentuates minor detail in terrain as compared to the traditional one. So here, for example, which location can I show you? Yeah, maybe this part over here and the same part over here that you can see. Okay, just a minute. Okay, so you can see that in this image it's not so detailed, but then here you can see it's more detailed, which means the multi-directional hillshade gives you like it takes into account the slight variations in each of the cell because we have multi points of illumination. So the advantages of multi-directional hillshade is that it presents an unparalleled view of the world's mountains, plateaus, valleys and canyons. Because the thing is, like especially in case of mountains, if you have a very huge mountain and if you just have a single point of illumination, that is going to hide a lot of features on the shaded part of the on the other side of the mountain. So if you have a multi-directional hillshade, then that regions can also be well accounted for. By varying the direction of light from 4 different sources, terrain depicted by the multi-directional hillshade is more realistically represented by balancing the overexposed and non-illuminated areas of the relief. Like the same thing that I've been telling you. The multidirectional hillshade enhances the expressionless regions and accentuates minor details in terrain as compared to the traditional one, which we just saw in this diagram. Like in this one, you don't have as many details, but when you come to this figure, you can actually see even the minute variations. By adding the hillshade layer to your map, you instantly provide clearer context and increased locational understanding of how your subject fits into the surrounding environment. So, thus, what we can conclude is you get more information and more details of a particular terrain if you, uh, you know, make use of the MDHS. So here what they're trying to tell you is mountains are like, they're very huge and it may seem like, that is how they have been before and how they are continuing to be, but that is not the case. They have been shaped over a long period of time, like millions of years, by the tectonic forces and the water erosion. So effectively in a few days time you will not see much changes, but then if you consider a change over years, then maybe you can observe such changes. So this relationship will get clearer when the hillshade is juxtaposed with the rivers or falls. So you can actually see where that variation is coming, because in regions where the falls are there, so that displacement of that area might be more because of earthquake events, fault movement and all. And if rivers are there, you know that the possibility of erosion is high. So when you juxtapose the hillshade with the fault map or the river map, then the information that you're going to obtain out of it will be more, rather than just looking individually at the hillshade map or the river map or the fault map. Hillshade is especially useful when displaying the relief of mountainous regions. So here you can see the Mount Rainier in Washington. One can almost feel the glacial remains on the surface of the mountain using the multi-directional hillshade approach over here. You can sort of understand how the glacier movement might have been, whereas in this case it lacks clarity and realism compared to the MDHS. Like both are is giving you some information, but the second one, the MDHS, is giving you much more detailed information. These are all examples of the MDHS. So here you have a satellite image that is given here. So, and the sun azimuth and the sun elevation is also mentioned here. Okay. So because this is 163, then what does that mean? Like if I draw here, just a minute. Okay, so if I'm drawing like this is north, this is east, this is west, and this is south. So same thing, it can be 0 degree. If you complete a complete circle, it is 360 degree, this is 90, this is 180, and this is 270. So in this case, you can see the sun azimuth is 163.3 degree, which means it is going to be somewhere in this quadrant. Okay, so which means it should be more or less in the southeast direction or the southeast quadrant. So the sun was in this part when this image was taken. That is what this information tells you. Okay. So the idea about the topography is not so accurate in this case. Or we have a false topographic perception phenomena in this particular case, because the sun's position is not the conventional one that we would consider. And because of that, this blue thing that you're seeing here, that is the Bhagirathi river. Okay, so this, because of this false topographic perception phenomena, it would feel like this Bhagirathi river, it is going on top of the ridge. See, because it looks like this is elevated, right? But that is a wrong perception. A river will not flow on the ridge, because river will always go in the valley, right? So topographically or geomorphologically, this is not a possible thing, and that is just because of this false perception. So how can we get rid of this false perception? So we exploited this shaded relief model, and we created a shaded relief model corresponding in a opposite, like the sun, by changing the sun's azimuth to 343.3 degree by maintaining the sun elevation. So now the sun illumination is from the northwest, and we can see that Bhagirathi is flowing actually in a valley and not a ridge. So that false perception has been well accounted for in this particular case. Okay, now what I'll do is I'll continue with the problems, and then we will continue with the week 11 lectures and a little bit of the week 12 in the next session. So I think uh, we will have two more sessions before this, like before your exam and before the course gets over. So yeah, anyway. So I have actually included the week 10 problems that was given in the assignment, because the solution is already out. So I thought we'll just revise that first. So which of the following cannot be modeled using a DEM, digital elevation model? You can just give me the answer in the chat. Yes. I know this is basically the same question that is given in the assignment, but it would be good if you can just revise it. That's why I've included it. So the answer is geology. The rate of change of elevation is called? I just want to tell you, like, when even for the exam purpose, I'm saying, otherwise you have to learn all the things. But for exam purpose, I feel sir has really focused on the slope gradient aspect thing since uh, some previous lectures onwards. So it would be better if you are very well clear about that particular topics. The answer is slope. The rate of change of elevation is called slope. What is the difference between slope and aspect? Yes. So if you have a hill kind of thing, you have a fall line, right? Where that topmost point is there and where it is decreasing. So slope is the gradient directly down that fall line, like how that is varying. While when you talk about aspect, aspect is the direction of that fall line relative to the north. So this is why I'm telling you, like in few of the previous assignments also, I've seen multiple times sir has included topics related to slope aspect and also the spatial interpolation. I'm not saying like this is my observation. I am not very sure like if he's going to repeat that, but I would suggest that you put a little more effort understanding these things. Slope can be calculated from the formula S is equal to B square minus C square. Is this true or false? More details about what? Values for this question, like the slope question. I think you are asking me about this problem. Okay, what is B and C? Okay, I think sir has given a diagram. Just let me check it. Uh, just give me 5 minutes. I'll just check it and I'll show it to you. I'll just open, just let me just stop sharing. I'll open that. This is given in the slope calculation part. So I'll just take the image and then I can show it to you. What is meant by the term precision? I'll definitely check this B and C. I've seen it in one of the lecture, I think, but I'm not able to recollect which one. So I'll check it and maybe in the next session I'll show it to you. Okay, so the answer is the level of detail at which the data is stored. So precision with respect to GIS is this, the level of detail at which the data is stored. What is meant by the term data quality? Yeah. So it is the inherent quality of the data as characterized by its accuracy, precision, bias, level of error, etc. Like the better all these things are, the better will be the data. When an error in a data set leads to the commission of another error, what is that called? One error leads to another error. So what do you call it? It's not cascading, it is propagation. Because one error is there, then the next error comes, so it's like gradually propagating. So we call it as propagation error. DEMS can be prepared from raster stereo pair, contours, INSAR technique, all of the above. Yeah, it is all of the above. Now, and one thing you also have to keep in mind, like I think that question was there in the previous session also. Like DEMS can definitely be prepared from all of these, but the most common technique used for DEM preparation is remote sensing. The shape of unit of DEM can only be. It is square because see the single unit should always be square. Okay, this was mentioned in one, I don't know, like the initial sessions. So the basic unit is always a square, but the overall thing can either be a square or a rectangle. So like what I'm trying to say is like you have, this is a rectangular thing, and then you have a square. Okay. So what this question actually is asking you is what shape should be this unit, like whether it's a square or a rectangle. So that single unit, it's always going to be a square, but the overall shape can either be a rectangle or a square. So the overall shape of this one is a rectangle and overall shape of this one is a square. The cell value of a DEM can have which of the following? Yes. So it can be positive, negative, integer, or even real values. The DEM is not based on which of the following? It's not based on discrete XY coordinate pairs. Can you like, did you understand like why that is so? The reason why it's not based on the discrete XY coordinate pairs is because the DEM, it basically represents the elevation as a continuous surface rather than individual points. So it's not always just XY, it's not points, right? So that's the reason why we say it's not a based on discrete XY coordinate pairs. Tessellation, it's basically, as far as I know, it is some kind of pattern that is generated, which is made up of like different, not just one specific shape, but different kind of shapes. Like for example, what can I tell you? In case of this digital elevation model, it refers to like how the surface of the earth is broken down into small uniform shapes to represent the elevation values. Like this, like we have these grids, right? Grids, and then you have individual cells. Like I'm just randomly showing you. So we have these individual cells. So this is a regular grid. So each cell, we consider it as a tile in the tessellation, and each of that will have a elevation value. Basically, you have to understand that it refers to how the surface of the earth is broken down into even further small shapes. DEMS generated from INSAR and LIDAR data generally have a spatial resolution between 100 to 150 meter. No, I it's false. It's not true. I'll just check the exact value so that you can remember. But mostly, if you remember, most of the available DEM data, uh, like available to the public, that is generally of 30-meter resolution. So it depends on, like it is available from 10 to 30 meter, but largely we have the 30-meter resolution. And the LIDAR, like INSAR, it's mostly like 30 meter, 10 to 30 meter, and LIDAR, I just checked, so that is like it can be as fine as 0.5 to 2 meter, or even more finer. It can be between 10 and 30 meter mostly. If of course it can change, like even there are 90 meter resolution also, but largely the one that we get, like free of cost, that is like in 30-meter resolution. LIDAR is even more finer resolution. Like that's what I just checked it. So it's saying that even in LIDAR, it can be as fine as 0.5 to 2 meters. Okay, so that's all the question that I have for now. Mm. Okay, so I've not really completed the week 11 lectures today because it's quite heavy and I had some pending from the last one also. So that week 11 plus a little bit of week 12 we'll take in the next session, and we'll complete the week 12 in the following session. Okay, so thank you for listening to me patiently. And I'll check on that slope equation, and I'll show, like, I'll find the figure and I'll show it to you in the next session. Okay, so shall I stop the session? Okay, thank you so much. We'll meet on Tuesday. So, thank you.